many integers. Okay? Why they are raised? No.
Right.
So, and that was a start for Rudy Kalman to study the story. But first guy was a guy called Leuenberger. Leuenberger was fighting just with his enemy. He told, okay, if I don't have enemies, what I can do? I can make a copy of this table. And what I will do, I will write down an error. An error E will satisfy the following equation. You see, I will do an error. So what does it mean, an error? X minus x. If I will do that, what happens? BU and BU will disappear. So I will have A, and E means AE means that I have ACX. So what I have to do? I have to solve a stabilization problem. What does it mean, stabilization problem? Stabilization problem means that I need to do that E goes to 0 when time is goes to 0. Why I cannot do it from the first moment? Because I don't know initial state. So this initial state, normally I am putting to 0 because I don't know I cannot measure x and I don't know initial state here. So that is why an error should go to 0. In this case, I will be able to control this, to observe the system at least when the time will go to 0. It is a good news or not? It is a good because what I can do, you know, let's say, how I can place eigenvalue or not. Have you studied it recently? So you know how to place eigenvalue. So what happens? There are two things, linear control, eigenvalue like that. And an observer, you are doing vice versa. But the story is the same. Because what do you need? You need A, B, and here you need CA observable. It is no problem. It's the same story, how you can do observer as well as you are putting. So, and this was 67, I think. and it was good, but there are enemies. What to do with this enemy and this enemy? Those of you which try to understand something about the history of control, they know that it was a lot of steps. In the end of 60s was a fight to study state space instead of frequency domain. As I've told yesterday, Rudy Kalman, which introduced this concept, were unable to publish the paper about state space in IEEE transactions. He published it in Transactions of Mexican Mathematical Society, and it is the most cited paper of Mexican Mathematical Society in all of the history. And then the concept launched. And then observers appeared. Okay, but Rudy Kalman was a guy from optimal control. And being the guy from optimal control, he thought, okay, I have enemies. These are my enemies. So what I have to do? The only I can do, I can put the controller forgetting without that, observer forgetting without that, but I have a freedom to choose the angular agent. How I can use such? I can use them to minimize the influence of force. It was his own. The point is that after a short time, people have realized that this estimation is good if you know these and this. So, but if we don't know them, so that is why in 98 and mostly in 2003, people doing the sliding mode control, they've understood that they are able to do a little bit more. What? You know, theoretically, when you are differentiating on the paper, you know the he told, okay, imagine that you have you are measuring the signal, but with the noise. So what happens? He told, okay, can I estimate derivative or not? Imagine what happens. Your real signal, you want to estimate it like this one. your sensors are giving you like that. So, question: how to estimate the derivative? Why it's important? Because as you can see here, the derivative is much bigger than the signal, isn't it? So kill yourself. Because if you would like to differentiate the signal, it will be so noisy that you cannot do nothing. So, but imagine that you have more or less good cells. The noise is not too big. Doesn't matter. Why? Because this noise is not too big, but see the difference in derivative. Because you need derivatives, so kill yourself. So, and Professor Kolmogorov told, okay, you still is able to do something if you suppose that you know the upper bound of derivative of the thing. F dot less than L. If F dot less than L, you can separate the noise, which has much more derivative, and than the signal. Is it clear or not? Because the derivative is like that, no? The function is like that, so derivative is corresponding one, and you can shape, and you can this is too much, this is too much, this is too much. And so you will have an estimation of the signal. So what he told, okay, here, omega, and this omega is something like delta. So the equation of your derivative will be 2 square root of 2 square root of delta. It is best possible. That's what you proved. And in the case you have a discrete signal, it will be the same with the discretization step. Okay? So this means that if you're a rich guy with a very good sensor, means 10 minus 4, example, what you will able to have. For the first derivative, for the second derivative, you should have something proportional to that. So what does it mean? This means that if you will have more smooth signal, you will have for derivative this estimation. So as smoother is the signal, better you can estimate. That's the story. Because for the second derivative, you will have something like square root of cube. Okay? You need a position sensor with 10 minus 3. You are pick out your illusions. That I am rich guy, I can have precision I want. It is not true. But what do you need? You need to find an estimation which is best possible. That's your goal. To have the best possible accuracy. Okay? So now, that's what I will speak about. So, yesterday and the day before, I talked about sliding mode. Now, I should start from the beginning. Okay, so good. Let's start. So, what happens? The first attempt was the following. Okay, I have a system. There is now it's just a simple story without enemies because BU is a control, we know it. So what we are doing, we are telling ourselves, okay, are Y variables good, interesting for us? No, because we are measuring them. So that is what you see. It was the 60s. Computer law was important. Now the difference between chips, between price of chips, is practically nothing with respect to doing and lightning. So that is what happens. Let us suppose that we have C space, we know, and orthogonal space, we don't know. Okay? So what we need? We need to separate the null space, the null which space unknown. And that's simple to do it using standard transformation. And so finally, what we will have? We will split the system for which we know here something. This part we know, it is part of error corresponding to what result we measure. And this story we don't know because it is in orthogonal space. Q1 is orthogonal space. So what we will do, we will make sliding mode in this part of the system. Because we can inject an error we are measuring. Injecting it in finite time, this variable will be dead because we are reaching it in finite time. And so what we'll have? Algebraic equation, as I told you. What is equivalent control is algebraic equation. So this story will be zero, this part. If it will be zero, so this will be also zero because we are making slightly more on it. So we can have an injection of this term. Nu will be equal to this. So what we will do, we will put it here. And if we will put it here, we will have reduced order observer in which L will be our real limitation. And so finally, what we will need, we will construct observer for reduced system for orthogonal space. And it will be so-called reduced order Nonlinear observer. Okay? Good, perfect. You are able to reduce the order. So that is why next step appears. So here we have an enemy. What is this enemy? Is unknown. Okay. Here we have the system. We are measuring the output for the moment without noise. And we are telling, oh guys, what we will do? We don't know the model. This term doesn't matter, but this term will kill us. So the answer is, will this definition of observability work or not? Because we don't know what the system. How to define a system which you are able to observe even due to the presence of what? Due to the presence of unknown of this. So what will happen here? It happens that what we will have. We have the table, okay? Are you lucky with the table? Me, yes. So what I will do? I will perturb my table, sorry. And if I will perturb my table, it will not move. So what does it mean? This means that even I have the equations here, and I cannot see nothing in the output, I'm measuring position. You see? I can conclude that velocity is also zero. Okay? What is an input in my system? Perturbation. What is an output of my system? Position. And so I'm measuring only what? Position. What I need to reconstruct what? Velocity. So I am able, yes, because I don't move. That's the point. Here is the key point. The key point that the system is strongly observable. What does it mean strongly? Even in the presence of enemy. This is my enemy. Okay? I would like to kill my enemy. So what I'll do, I will see if my system is strongly observable or not. If it is so, mechanical system is strongly observable, because if I know position, I can differentiate and have velocity. And the acceleration, it is Newton's law. So if I know position and velocity, so I can write Newton equation or later Lagrange up to your education. Okay, is it clear? So that is why. What's the difference between simple observability and strong observability? The difference is that simple observability without enemies. Strong observability is observability. I am so strong that any enemy doesn't matter for me. Okay? I don't know if it's clear. I'm so strong.
So the so strong is essentially so strong, right?
Yes. Strong means that even I have perturbations, I still live. So the enemies are not important. So, and then the next standard notion comes, strong detectability. So that's something like China's philosophy. Do you have an enemy? Good. Let's please, and you are living over the river. So, okay, let's go, please go to sleep and give him pass. And sleep till the moment when his body will come down to the river. So, what does it mean? The system, normally, and it is true for any system. What is a model of the system? Is a small part of the dynamics. What's the difference between system and model? What's the difference between system and model?
Some part of the system.
Model is simplified. Model is some simplifications. System is very, very complicated. As the model is simple, why it works? And where is the art of engineering? It works because the engineers are clever. They are modeling the most important part. And the rest is follow the most important part. So the point is that you have to understand what you need to regulate. This is the art of engineering. Art of engineering is to make from one simple model, from the other side, that it is described well the phenomenon you'd like to study. So that is why normally the system is not strongly observable, never. It should be. This means that parasitic dynamics, parasitic means that you didn't take into account in the model such a dynamic. So if you are not taking into account the parasitic dynamics, it will die as soon you So every time you get, it is not a big deal to make very complicated model. What is a small model, but which reflects what you want. That is why what the rest of the dynamics should be stable. And what to do? Okay. And you can, if you will wait, the body will come down to the river. So what does it mean? This means that the rest of the dynamics is stable. You can, if you will wait, you will tell exact estimation of the state. Okay? That's the story. So that's the difference between strong observability and strong observability. So now, What's the problem here? And you have an if you know in your control, you know that the other criteria of observability is that you can construct this matrix CE minus I and C, so you are making extended system, and you need to ask the code that this extended system has having the full run, so it will don't have what invariant zero, so means false. That is why what happens here. If you will see, you need to extend here the state. Why? Because this state responds to your element. So, and this is matrix n plus p rows, and your enemy will have here, maybe you have less than m or m enemies. So extended matrix will be m plus, let's say, w will belong to some q, q and q more p more or less of the q, because if you will have less output than enemies, that's for sure. You have more. You have less soldier than your enemy. It is difficult to deal with. So that is why what happens here. We have here we have n plus p rows and n plus p plus q cows. But anyway, you can find the rank of the system, which will be n plus q already. So, and what you need to ask the bot, if they have or they don't have stable or even don't have eigenvalues if you'd like to have observability, not the stability. So let's do the next stage. How to in a we see it is a way to grow up. It was necessary to have 15 years to understand how to deal with the system with uncertainty. So after 15 years, people have understood that there are criteria for such systems for which they are strongly observable or strongly detectable. So, what do you need to ask from the bot? First of all, the system does not have invariant zero. Second, that you have P and P outputs, and here I have M and not P, M because now I don't have it on and I have it. But, so what happens here? It turns that the system can be split in 3 parts. Why 3 parts? Because if you have relative degree 1 with respect of unknown inputs, with respect to measured output, you can split the output in two parts. One which is contaminated here, and the other one which is not contaminated. So you see here is contaminated, and here is not. And here is orthogonal space, which we need to estimate. So what we have to ask from the board? We need to ask from the board that all contaminated, all unknown parts, all unknown inputs will be spaced out, because you know them. It is not a big deal for you. You don't need to know them. And the rest should be observable. Even you don't have Y1, all of your outputs are contaminated. The rest of the system should be observable. If you still have some outputs perfect, you can use them. That's the story. So, in this case, you can construct observer, at least like Leonid one. And what is important here is this one. To do that, you need that all of your unknown input will be in the space of measured output. If it is not so, you get that. Why? Because if it will be here, so it will not. Okay? That's the story. So, is it very strong supposition or not? Unfortunately, it is too strong. Why? Let's return to mechanical system. Okay? Mechanical system, it's like this. Only perturbations or unknown things are in the forces, because the first equation is just a definition. What is the definition? That position, velocity derivative of position. No changes here, not perturbations here. So you are measuring what? Position, 1, 0. Where are your perturbations? Here in forces. Okay? That is why you have 0, 1. So what's product? 0. Doesn't work. So you need what? You need differentiate, and you need once more to differentiate. That was a final initial point for me to study the phenomenon. So here, what I'm telling that if relative degree is higher than 1, because here is 0, so you need to have relative degree 2 in mechanical. So in mechanical system, all problems are in the forces, so you need to differentiate. No chance. So, yesterday I told that we have a dipole, looks like PI control, but this dipole is perfect. Why? Because he gives you a convergence not to position, but also to velocity. It holds super twisting algorithm, and that's how it works. You see, this is the P part, and here is an integral on sine parts. PI. So finally, what you will have, all the inputs will be given. And what you will do, you will choose this L in order to make it 0. So is it possible? Yes. And moreover, Professor Levant used here homogeneity. And homogeneity means that the weight of position is 2 and the light of velocity is 1. So if you have here a noise delta, here you automatically have square root of the. You don't need to do nothing. You will have asymptotically best possible precision in the presence of the noise. That is why I didn't consider the noise, because I know that I have a better estimation in the, for the worst case. That's the point. That's the key point I've started with. So then, finally, what I can have precisely a best possible estimation, and moreover, you see, I cannot take into account the spring in mechanical system. Why? Because I'm measuring position, and spring normally is what it is position, proportional to position. So that is why you see, in observer, I can neglect some part, and it L could be not full acceleration or maximal acceleration of the system. It could be less. Why? To have better estimation. So that is why I will tell you now how it works in reality for arbitrary order system, giving you an example of the system with uncertainty. So imagine now that I have perfect differentiator, but I have an uncertainty. What will happen? I will differentiate. I will put Cx, Cx dot, and etc. And I will have this one. What's the problem? The problem is that I also have enemy here. So if I will continue the process, I will be wrong. So what does it mean? This means that to have estimation of the state, I need to ask the what? That all of these terms will be zero. If not, I cannot know. So that is why what is invariant zero is precisely a condition of relative degree. I can have uncertainty just in the last equation. Otherwise, it doesn't work. Here is the proof. So, and this is sufficient and necessary condition for the system to be strongly absorbed. Relative degree at 10. So now I will return to my table to explain how differentiator works. You see, standard sliding how it works. What I'm doing? I'm doing the following. I have a function, and I need to find a derivative. So what I will do observe of derivative. Okay? So, but I should suppose that the derivative is bounded. If it is unbounded, so it will be poor noise. Okay? I am putting myself the upper bound of derivative to keep out. It is a kind of filtration. I'm telling, okay, this is not passed. So if I will put such an observer, what will I will have? I will put an error. And then I will tell, okay, if I will put an error, I will have such equation. And if this gain will be more than upper bound of the derivative, I will have sliding mode in finite time. This term will be the same as this. What's the problem here? This term is what? oscillating. It is fast oscillating. If it is oscillating, what I need to filter it out. Otherwise, it will not work. That is why I need the other story. And what is the other story? I need the dialogue. The dialogue called supercritical. So what happens here? Here, I have the other restriction. I have the restriction not only on upper bound of the derivative, also an upper bound of the second. If I will do so, I'm able to make the more deep model of the system. Because here, before I had a first order model of the signal. Okay? Now I will have second order model. So to do that, I need to suppose that the signal is a little bit more smooth. It all next stage was even very much more important. Why? Because it is done, of course, in my team. But the idea is not one. The idea is, okay, I don't know the initial condition. I don't know them completely. So, first of all, I was waiting. If I will convert in finite-time, that's perfect. But the domain, I should know in advance. If I don't know the domain, which is for observer normal, so what I will do, I don't know, because I don't know the time where I will converge. If I don't know the time I will converge, it is very wide. Because the first idea, the very first was, okay, imagine that I'm flying from Dammam to Mexico. So, and I don't have an information where I fly. If I will have great data about my speed, I first will go to Antarctica or to Australia, and then down back. So that is why what I will do, what I have to do first. First of all, I need to wait. Then I will have correct data. Then is it clear? So that is why it was necessary for us to be sure that we will converge in certain time and then to start. Okay? So that is why it was necessary to have so-called uniform convergence time. And we've made uniform, or then the other student that might call it fixed time convergence. That's what we've done. And so you see what the difference with the standard supercritical. Here my table is leaving. Here is P part and here is integral part. Okay? Here we add something. Why? Because we would like to have a convergence which does not depend on the initial condition. So we can be extremely far, nevertheless we will converge in the time I need. So what I can do something which is not only convergent, it should be escape from infinity. So someone read the differential equation on Hallel book, chapter 3. Maybe some of you passed nonlinear control, isn't it? If you pass nonlinear control, what happens? You know that the system should be lifted. Okay? This term is not lifted. Why? Because the derivative is 1 by square root. If you will go to infinity, this term will be not lifted. Because if you will differentiate, you will go still to infinity. That is why, if you are putting it with the correct sign, you will skip as well. You will write finite-time with this term. So it is combination. So what I give you here. Normally, what happens here? You do the following. Every time you have alternative. You need the highest precision if you have linear, for example, observer with an unknown. What happens? If you need, for example, x equal or minus px plus drop w. So where is an equilibrium of this system? What is W by K, isn't it? If you will put inside of X W by K, you will have equilibrium. Okay? So now, what you are doing is to have less error, what you will do? You will draw the K. And here it will be an error. Okay? Now, you have noise. What happens with the noise? If you will grow up the K, the noise will grow up. Isn't it? So, what you need to find a compromise. So, is it good? No. Maybe you will have the better couple to be married. It is not too bad. So let's see. And the better couple is precisely higher than sliding what you can see. Because for any level, because I will explain you. For any noise, you need to have another curve. And so, and compromise will be different. Okay? But for sliding mode, doesn't matter. Because for any small noise, it will be the same. So that is why you need just to check the noise, because you will have finite-time convergence. And it is theoretically precise. That's the key point. That is why we've invented arbitrary order differentiators. This is example of the first order differentiator. And you see standard solution. Initial conditions growing up, and the time of convergence is also grow up. So what does it mean? It means that you can make a couple of times around the Earth when you will have correct data and you will fly them. Otherwise, you need to make a restriction, and this restriction was given here, and you see it has asymptotic, and this is upper bound of time. This is red, and it doesn't matter. It is logarithmic scale. How big you will have initial conditions? That's what I explained in the first work. Okay? It calls fixed height convergence. So, and this is a version of arbitrary order differentiator. And here is uniform arbitrary order differentiator and automatic shifting. So this term, okay? It calls B homogeneous. Now, return to our observability. Our observability problem now is married with differentiators. Okay? So what we will do? We will consider the system with unknown inputs. And so what happens here? What happens here is that you have the system with relative degree evolving class from observability. And then no, you need to work with differentiators. And as less is differentiator gain, more is what? Precision. So that is why the first idea to make differentiator was the following. Let's do the following story. Imagine that you are a king and you are going to kill the animal. What you have, you are a king now. You don't need to walk too much. You have special people who bring the animal nearby and you will just kill it. Okay? Is it clear? An example? So you need to have special guys which bring your animal as in the reasonable distance, and you will just kill it. Okay? So why I'm telling you about that? Because here what we offer is a combination with linear absorption and differentiation. It will be cascade scalars, cascade structure, which first make which is kind of observability, Leonid. Leonid brings you an error in the vicinity of uncertainty. And then you can bring a line waiting for, and then what happens? You will wake up. I mean, differentiator will wake up and kill them. That's the story. I don't know if I didn't tell you as an example, but it is how it works. So I didn't put here a cascade scheme, but you can understand. First, I'm putting Leonid, and then I'm switching on differentiator. So finally, the animal killed, and finally dead. That was the first idea. Now we have developed the observer without cascade structure, but that's not what it is. Just to understand how it works. And so what happens in general case? In general case, what we do have, we have a block structure for each input. You have for each output you have something to kill, but this what you need to kill is every time concentrated in the last line. So, and you can have the system which is observable. From the observable in finite time, you will have. And that was my first paper group. And then, what happens? You see, what I need here, that it will be all of the space here. And it will not happen every time. So that is why we need to use some little bit more clever strategy. And more clever strategy is the following. Okay, what I've told you, we need to make derivatives. But we need to do it in the clever way. So what we will do? First, we will make a derivative of output. And then some uncertainty can appear. So we have to do clever differentiation. In which case, we should differentiate in the direction in which you don't have uncertainty. And so that is why you will differentiate in orthogonal space to this. If you will do clever, so you will obtain the first derivative which is not affected by uncertainty. And you can continue the story like that. So, and finally, you will do the same story here for the next derivative. You will also differentiate in orthogonal space. And finally, you will cover all of the space and you can make an observer, as I told you. Means hunting kill, at least. So now what we will do in the case of strong observability. I don't know what's. I will just tell that recently we are publishing the papers with Professor Jaime Moreno and our PhD student. Sometimes they are publishing without me. We are making the observer for LTV system. LTV is a little bit more difficult story. Why? Because LTV, let's say, you need to have special matrix of observability because you need to differentiate not only the state but also the matrix. If you're interested in, you can do it. You can see our papers. It's not difficult to find them on the internet. So, what I would like to tell you is about general case. In general case, you have a series of spaces. One is strongly observable, which could be affected by uncertainty. The second one is weakly observable. What does it mean for me? This means that it is observable, but if there is no unknown input there. And the first one is just unobservable. So what will happen? You will see the system in such a way. You have strongly observable part which is affected by unknown input. The second part is measured but unknown input. And the third part is not observable, but it is stable. So here you are able to observe exactly. Here, if you will not need differentiator, you will observe asymptotically. And this part should be stable itself. If it is so, if H3 will be stable, so you will be still observable. So, and that's how it works, how we designed the observer. So then, what will happen if we would like to observe all of the state, but part of it? If it is so, what we will do? We will do the following. We will have a decomposition of the system for which unobservable state can have stable and unstable eigenvectors. So if it is unobservable and if it has stable and unstable eigenvalues, what we need to ask for the output? We need to observe. You need to observe just the states you need to observe. You are able to observe the states if and only if you will not touch an observable zone. If you will touch an observable and unstable space, it will be bad. Otherwise, you can still work. So, on nonlinear case, it is just a play with relative degrees. You know that nonlinear system, they do have normal forms, and if you will transform the system into normal form by Isidori with respect to measuring input, you will have the same. Maybe you know that in state of multiplication of CA and CA matrix, you will have 3 derivatives. And with these 3 derivatives, you can have the same forms. Finally, the form of the integrators. And then you will make the same tricks that I made for linear systems. That's the same story, more or less, just with the effects of nonlinear. So, now, about left object. So, yesterday I asked you asked me what to do with unknown name. So, it is not enough to have observability, even strong observability, if you have unknown name. In your case, it's even worse. Why? Because you have 2 unknown inputs and just 1 output, isn't it? So you can evaluate with derivative for just 1 signal or 1 zone. It is bad. That is why you need to understand what you are doing, what you really can or you really cannot. And that's precisely the point. And you can see here our first paper in Automatica 2013, how you can deal with the estimation of unknown inputs. So, I don't know what happened. I returned to So, I will tell you just what final stories because, you know, I think that it is enough material today. So, the next stages was two. Stage number one. What to do with hybrid system? Because what hybrid system means? It means that you are changing models from one point, and then you are going to the model, and then you have the other model, and the other model, and the other. So imagine that you have walking robot. It is very difficult to follow one, because when you are walking, the trajectory, what happens? It is continuous, because you stop, and then you have another. And this is continued in the way. So what is a restriction? A restriction here is that you should end observation at the moment you will pass. Otherwise, your error will be wait and goodbye my work. Is it clear? So that is why the first idea how to apply the story is what to do precisely writing what we call or either because the main advantage is that you are able to ensure that you will reach theoretically precise application. That's perfect. And what is that what is the next stage is what is another way to see it's fault. Why? Because what does it mean fault? Fault means the change in the structure of the model. So, if your system, if you suppose that the errors are not, the error appears after certain time, not what we need to ask the what that in the time between errors, between faults, the observer will converge. If it will converge, you can estimate what you can estimate. The next stage was the fault. And you can find in the literature as it was a topic of my PhD editorial, which is already a full professor. But so he's publishing a lot of papers based on all control. And so it is rather successful. So, and there are many of them because you know there are a lot of types of hybrid. And in any of them, even you don't know discrete state, you can also identify. For example, if you have a system and you don't know which one will work, you can put an observer and identify which one will work. That's enough. So there are plenty of work that is running so fast. And let's see, that's more or less the story I'd like to finish because I feel that I'm pressing you a lot and you are tired and try to make a job, but I feel that you're sorry for that because the things I'm doing is not completely. So please, if you are still not so tired, ask me.
In slide 20, there was an assumption that it was, I think, more actually.
I cannot see the numbers here, you will stop me. It will be before or after?
I think it's like the assumption.
This one or what? If you are, what you are mentioning, this? But what is the, what is that? So you made a great story.
Sorry, I misread that one. So there was an assumption that you can go.
How?
Yeah, this one. This assumption f minus x1, the estimate x1 is without f dot minus x. Means how the assumption can.
This story is a second order sliding. What slide, second order sliding means? First order you converge to position and finite. Second order is if you converge to position and velocity simultaneously. That's what you are asking about.
Yeah. That's the assumption.
Yes.
So I could not get it.
Yes, that's let's say. First order sliding mode is like that. You have x, you are putting x dot equal to sigma minus sigma x, and you converges in finite time, and then you are here. Okay? Second order sliding mode. You see, we are changing the order of the model. We have second order mode. So what we are doing, we are doing and v converges to 0 in finite time. Then does this means that x and x dot are 0 in finite time. So that is why both of them converge. And if x and x dot converge, e and e dot converge, you have simultaneous. We are extending the model. And we extend the model, it is difficult because we need to ensure that it is still. What is the difference here? That you converge even you extend the model. And that was a dialogue. I told it why it's dialogue. Because it is clear to understand how it converges with finite time if you have size. If you have a dialogue, it is not easy. That is why we got that. Because it's PI. PI, what does it mean, PI? That you keep convergence even you have constant acceleration. And here, because your PI is nonlinear, you have integral from time function, you can compensate when you are doing, that's a secret. If you are doing like chi integral x from tau, e tau, 0 from t, you are compensating the constant. Because linear terms compensate their derivative at 0. If the derivative of your perturbation 0, this story will make you stop stable. Now, imagine that you have function. If you have function, it is not the same story because you put EI, but signum x. What does it mean, signum x? Signum x means that all you can cover by signum, and signum is what? It is any function bounded. You can cover it. The only you need it will be reached because it's so easy. So that's all. That is why it's direct. Because it's not traditional. If you have PI, you are compensating point. If you have I from sine, you are compensating what sine is equal. You compensate inclusion. I think you've been in my first lecture. You understood that what we are doing, we are killing inclusion. So we are policemen beating the victim. My victims, I will able to beat with them. I can only fight also.
Thank you.
Okay. Some of the comment we often receive from the viewer side that when we use this exact differentiator, we assume that the derivative of, let's say, if you assume
The next derivative is bounded.
Yeah, bounded, then they say how you are taking this liberty to know the value of f dot and f double dot to be known. So if you know, that means you know about the system, and if you are taking liberty.
No. Wait, sorry. What happened? You see, for any system, what do you know? You know the upper bound, your measurements. Or, for example, if you have mechanical system, you need the first derivative. But if you have the car with infinite acceleration, you know what? I know the maximum acceleration of the car. So that is why, of course, you have to know. But let's say, the more fun story, if you know not acceleration, but jet from the door, what knows? I know. So that is why you will have clever engineers know. That's the story.
Then we have to put a remark that, okay, why we know these values. So we have to justify every time when we use this kind of observer, we have to justify the reason why we know the value of it.
Let's say, you cannot control, that's what I told you. You cannot control completely black box. You need to know some other problems. And the only reason to tell that in many real systems, all things are bounded. And so it's from the nature of the system. Okay, or the other story. Okay. Give me alternative. I need to filter it out. Yes? So what I need to filter? So it is simple body problem. But a simple body, no? If you have body, you know that the best filters are working like that, no? The body form, isn't it? So you need to tell, here is my cross frequency. I need to know it and start to filter here, isn't it? The same story. I need to know something. If you know the filter, you know the upper bound of the derivative. Otherwise, your filter will not work. Without knowledge of the upper bound of the derivative, you cannot do nothing. You have to filter. What is the story? Of course, higher order slightly more differentiator is a filter. No. But it is another way to put a cross. No, if I don't. So for mechanical system, it's simple. You are telling, okay, right. You have an infinite acceleration in the if not, I can today. Okay? And even as a rocket, you don't have infinite acceleration. You have combat acceleration, and your velocity is going proportional to the time. So, I don't know if you've seen what I do. I have seen how the rocket is started. But then from Mars, it is typical Russian names. And I, once in Baikonur, the base for which the guy started. And it started really, really slow. And in 80 seconds, it gets 8 kilometers per hour. And that is like it is around 80 seconds. And that was precisely one of the projects I just did. Because, imagine that my metabolism is good. So, can you imagine the metabolism of shuttle? So, just a question. Can you imagine how much gas is burning the rocket, which is bringing shuttle to the space? How much gas? You know?
For the tons, or more than a ton.
3 tons per second. 3 tons per second. So, and it is a high temperature, and can you imagine how you can burn 3 tons per second? This is a story. And how it was done in Apollo. In Apollo, in the first version of the shuttle. You see, if you burn 3 tons per second, you've seen 2 tanks. They are starting with, and this tank has 240 tons. 240 tons. Now imagine you are burning 3 tons per second. So what happens with coefficient? Because they are on the left side, you should divide them. So they in the first version, they made 80 times schedule. Game schedule. Why? Because you need to reschedule the game every session. It is not simple engineering problem. This why? Because they are burning 3 tons for the second. So, and that finally, I think, not to give human control. So, it is very simple. Not a simple task, but intuitively it's simple to understand. Only non-linear controllers is able to do. Because linear change every short time. And so, in the last stage, what happens? They are getting off of the tanks, and then the second motor starts. Okay.
About the rest of it. When you talk about predefined time or fixed time, how can we have that defined and something from different issues?
That's precisely the story. You see, I can explain you in two versions. Would you like to see? I'm able to write here an equation, and you will see how it works on the level of equation. And then I will explain you how it works on the level of intuition. Okay? Is it okay for you? Okay, let's do. You need a system to be converged in finite time, like here. if you will do it, it will converge in finite time. Why? Because the gain is infinite, okay? Why gain is infinite? Because the derivative of square root is 1 by square root, isn't it?
Yeah.
Now, you have to escape from infinity also in finite time. Because you asked me for, let's say, fixed time conversion. So what I will do, I will put this one. At infinity, this term is not Lipschitz because I still have square root, and when I will have square root in infinity, it will go to infinity. Is it clear? Now, let's rewrite the equation that way. Okay? Now we need to integrate. Should I tell here something? Or it is clear? It's just change of value.
Yeah.
Okay? So what happens? Why? It is clear. Here is 2z, and here I just what I put it here like square root from 1 plus x, and it corresponds to that. Is it clear?
Yeah.
Then okay? So what happens here? Imagine that when I will, t will go 0, x will be arctangent v0. So what does it mean? This means that two arctangents of z from t minus two arctangents 0, z0 equal to c minus t. So equal to minus t. So what happens? It happens that this function is bounded. Yes? What is the upper bound? P. Arctangents is bounded by what? By P. When u will be 0, when this story will reach this one. Okay? So this means that two arctangents 0 will be converted from square root of x 0 will be your convergence time. And it will be less than P. Done. Now, intuition behind. What's the intuition behind? The intuition here is that you have here finite time convergence and here finite time escape. So finally, you will converge, and the upper bound of your convergence is by P and bounded by P. Now, it is not what I've taught. I've taught a little bit more because you asked me to make the time prescribed. So I have 2 gears to do it. One is to put here k squared. The other one to put here k squared. Okay? What will happen? In both cases, I can reach the time smaller than p. P divided by k. But here is very important point. If I will put t here, I will make a precision worse. But I can reach infinite time. If I will put t here, I will save the precision of this, but I will make worse this story because I will have a big overshot. So that is why optimization problem is still exists. Because that is why I've made my last paper making a maps between time convergence and precision. Up to you guys. And also the field is overshot. So enjoy.
Yes. So the students who have some questions and they want to discuss more with Professor Fridman, they can come to our department, CI department, and office there. And we have scheduled a discussion, or maybe the graduate student can come to me from 1:30 to 3:30. We have a time slot. So
All of the next week,
yeah, and he will be here.
but also today.
Yes.
So it's better to take benefit from him. Like a senior most and the leading professor in the field of sliding movement. So we are very fortunate that he coming here all the way from Mexico. So for us, it's a great privilege to have him. Please give him a round of applause.
We have also refreshment.
Yeah,
Sir.
so we're not able to inform, so there's a refreshment outside.